I want to close this portion of the lecture with a revisit back to the idea of systems of linear equations. So suppose that we have n variables and we have m equations. Then we can write that as follows. X2, and we have n variables. Okay, and suppose that equals some number on the right hand side, b1, where the first number here represents the equation, the second number here represents the variable of interest. So we have m of these equations until we get down to the last one, m x1 plus am2 x2 plus amn xn equals bm. And so there you have it. We have a system of linear equations. But given all of our discussions on the matrix algebra, we should now reflect upon this system. Remember what each equation represents. Each equation represents a shape in n-dimensional space. If we had two variables here, then it would represent a line, and each equation would represent a unique line. In practice, each equation usually represents a constraint of some kind on the variables. We will see this later on when we get to our optimization lecture, but with this stated, we notice that each equation, okay, that represents something very practical like a constraint. Geometrically, it represents a line or a plane in three-dimensional space, or in n-dimensional space, we call these what are referred to as hyperplanes. Whatever you want to call them, they're linear equations, and linear is nice. Now, what you may notice here is that you have dot products. So if you define a matrix A as A11, A12, A13, all the way to A1n, and you do that for the M, and you do that up to the N, and you define a vector X, and you define another vector B, you'll notice that we can actually write this system of equations in very compact form. This is just simply equal to A, the matrix A, times the vector X is equal to the vector B. And we have numbers here, we have numbers here, and this is the unknown. Now, in the instance where m is equal to n, A may have an inverse, in which case, if we can magically find what the inverse of that looks like, then as it turns out, we can multiply both sides, and we can obtain very easily what the solution for x should look like by just simply multiplying b times the A inverse, and life's good. On the other hand, if A is not square, or A does not have an inverse, then we still may be able to find a solution for x. But what we do is simply we start with the Ax equals B, and what we do is we create the augmented matrix AB. Remember augmented matrices? That would basically just be like putting all these as a last column here with a line next to it. And when you do that and you apply the Gauss-Jordan algorithm to that matrix, then what you're able to get is a solution of x's. I'm not going to go through this. I think I have some pretty decent examples in the notes to illustrate this process. But hopefully what you should understand from this process is that we can represent the system of linear equations as a very, very simple matrix equation. Now, why is all of this important? It's important, especially in the field of statistics, because suppose I have the area of statistics where this is an output variable and these are input variables, and you do the reverse. Suppose you don't know what these are, but you happen to know your X and your B's. In which case, what you can do, or I'm sorry, these represent your X's, and this represents your Y's. And the X's here actually represents coefficients. Well, here, each row would represent a data point in my data set, and each A here would represent some characteristic about the individual. The question is, what's the equation that relates the X's to the Y's? Well, if you have this matrix format going for you, that's very easy to find, which we won't get into this instant, but basically the process is that you apply the fundamentals of linear algebra to fit the data to the model. So in a nutshell, these are the fundamentals of systems of linear equations. We solve them by applying Gauss-Jordan elimination to the augmented matrices, or if we have an inverse of a matrix, we just simply multiply the inverse by the corresponding numerical vector.